At JEE level, from electricity topics, alternating current circuits is one of the important most chapters what we have. Almost every year he is giving one question from this topic, which of course is going to be of 4 marks at mains level. So if you people are totally confident about this topic, every one of you can score those 4 marks. AC circuits, when we deal with, what is alternating current first of all? The current of which the magnitude varies with time and direction reverses at regular intervals. That's what we call it as alternating current. In the same manner, the EMF of which the magnitude that varies with time and changes its direction at regular intervals, that's what we call it as alternating EMF. Generally, while representing this alternating current and direct current, the general representation will be, for direct current will be having the peaks like this, all positive peaks, no variation in the polarity of them. Thereby, we call this one as DC or direct current. When we come across the concept of alternating current, a sinusoidal wave we used to represent it with. So you are finding positive and negative polarity variation. It's a sine functional wave we represent this one with. So the major difference in terms of graph between DC and AC we can show this way. Now at regular intervals, the polarity is going to be varied in the case of alternating current, whereas in the case of direct current, no change in polarity that is going to be observed. And we all in fact know alternating current or alternating EMF, we either can represent in terms of a sinusoidal waveform or a cos function as well. General equation when we take for alternating current, I can be written as I naught sin omega t. In fact, we all can understand directly this I naught is called peak value, or you can even call the same as maximum value of current. That is what actually we call it as I naught. Whereas this I whatever we are finding here with respect to t, that is the time, what is the value of current we used to measure using this equation. Therefore, this I is to be called as instantaneous value of current, and sine is representing the function of it, and omega t is generally called the phase. So when we talk about I naught, that is the maximum possible value of alternating current, whereas I depends on t. Thereby, we call this one as instantaneous value of current after certain time t. What is the value of current? If at all we want, we directly measure using this formula. Exactly in the same manner, E can be written as E naught sin omega t. Once again, one can understand E naught is either peak value, or you can even call the same as maximum value of alternating EMF, whereas this E again is called as instantaneous value of EMF. So this is the version generally what we used to take. In place of sine function, we can even represent this one by cos function also, because the variation is harmonic variation. Thereby, we can represent by harmonic functions like sine function or a cos function. So this is the basic equation or the general equation to represent alternating current or alternating EMF as such. While taking up alternating current in any circuit, we prefer considering two different values. One we call it as the average or mean value of current, and the second one we take that one as RMS value or virtual value of current. Exactly in the same manner, while considering alternating EMF also, average value and RMS value are the two different values what we used to consider. What is this average value of current or average value of EMF, alternating current or alternating EMF? Average value generally be defined this way: it is that amount of current which, when made to pass through a circuit for half the time, produces the same quantity of charge as produced by AC in the same circuit. Similarly, when we consider RMS value of current, it is that amount of current which, when we made to pass through a resistance, produces same amount of heat energy as produced by alternating current in the same resistance in the same time. When we consider these two, this AC voltmeter, AC ammeter, all these meters, they always used to measure RMS values of voltage and current only. Thereby, RMS values are very important in this chapter. So what exactly is the formula for average value of current? We can write this one average or mean value of alternating current. What is this mean value? We can rewrite this one: I average is equal to 2 I naught by pi. Similarly, E average, we can write this one as 2 E naught by pi. In fact, one can understand directly 2 by pi, that becomes 0.636 times I naught. We can write the same value. Similarly, 0.636 times the value of E naught. We can write the value for average EMF. So one is average value of alternating current and one is average value of alternating EMF. In reality, how to get this particular formula? A derivation, of course, we have for that. Let me just remind you, even the derivation, how to just get the same equation what has been written here for average value of current and average value of EMF. When once we can derive one value, similarly you can understand the second one as well. That is the advantage what we have in this chapter. So let us consider this average value of current first. Let us derive an expression for average value of alternating current. I write average value, that also is called as mean value of alternating current. That's what we just want. We in fact know I is equal to dq by dt. That formula of course is a direct definition for current, rate of charge that is flowing across a conductor. Cross multiplication of this one gives you dq is equal to I dt. But when we are talking of alternating current, this I can be written as I naught sin omega t dt. That I naught represents the peak value of current there, omega t is the phase and sin is the function. So we can say dq is equal to I naught sin omega t into dt. Then I just want the value of q out of that. This of course can be taken up by integrating it. Integrating between the limits 0 and t by 2. For half the time we used to define this value of average current. So 0 to t by 2 I naught sin omega t dt. I naught being a constant, you can remove that one out and we can understand well sin omega t, the integral value would be minus cos omega t by omega between the limits 0 and t by 2. Now check the next step over here. Q now becomes I naught by 2 pi by t. I can write in place of omega. We can understand well omega is angular frequency. That's 2 pi by t, the formula where t is called time period. That into you are having here minus cos 2 pi by capital T into small t between the limits 0 and t by 2. So you can rewrite the same equation this way now, I naught t by 2 pi into minus of cos of 2 pi by t, you can write cos of 2 pi by t into t by 2 minus cos 0. We can all understand straight away this t getting cancelled, 2 getting cancelled, cos pi becomes minus 1. Cos 0 degrees also is going to be 1. So minus 1 now becomes minus 2, minus of minus that now becomes plus 2. So what you can get for Q, you check it. It is I naught t by 2 pi into this entire value now becomes 2. 2 gets cancelled. You will be left with Q is equal to I naught t by pi. That is the equation what we can get from it. I naught represents the peak value of current. T is a time period. Pi being a constant over there, of which the value is known to all of us, 3.14. That's pi radian we people are talking about. Now we can write Q is equal to I into T. We are discussing the concept of mean value. Therefore, I write this one as I mean into the time that is taken is half of the total time period, that's t by 2. I now can take this as the second equation. Observing carefully, this is the derived formula for charge. This is according to the definition, the formula for charge in terms of current. Now just equating these two, whatever the required formula we want, we directly can get. Check this equation now, I naught T by pi. That now is equal to I mean value into T by 2. So T getting cancelled here. What is now left? Mean value of current now becomes 2 I naught by pi. The same equation already we have taken up earlier, but this is the method of deriving that equation. So 2 I naught by pi, that's what we used to call it as mean value of alternating current or average value of alternating current. Already I have given you, this value can be written 0.636 times the value of I naught. Exactly in the same manner, that is similarly, the value of alternating EMF, mean value of alternating EMF, we can write the same as 2 E naught by pi, which again can be written 0.636 times the value of maximum EMF. So these two are two important equations one should remember. So whenever we deal with average value or mean value of current, the basic formula will be 2 I naught by pi. Similarly, the value of mean value of alternating EMF, we can write that one as 2 E naught by pi. So 2 I naught by pi, 2 E naught by pi, these two are two formulae one should remember. In the same manner, what is RMS value of alternating current? That RMS value also is called as virtual value. So what is RMS value of current and what is RMS value of alternating EMF? Just recollect those two formulae as well. If I write here IRMS, in other words we can call it as IV, V for virtual, that now is going to be I naught by root 2. I naught is maximum value of alternating current. By root 2, this value is equivalent to 0.707 times I naught. So RMS value of current whenever we want, we can represent that one by this formula I naught by root 2, which as well is equivalent to 0.707 I naught. Similarly, when we write ERMS, that will be written even as EV, virtual value of EMF, that now can be rewritten as E naught by root 2, which also can be written this way, 0.707 times the value of E naught. To derive these equations, we consider the equation for heat energy developed or produced across a resistance R. For example, when I consider dH is equal to I square R into dt. But when we consider the value of I in terms of peak value of alternating current, then we can represent this one as I naught square sin omega t, right, whole square, that of course I naught sin omega t whole square into R into dt, that we can write it as dH. We can even rewrite the same this way, dH is equal to I naught square sin square omega t into r into dt. Same you can even write it like this, I naught square r into 1 minus cos 2 omega t by 2 into dt. Now dh can be written this way. Now by integrating this one, we will be getting the value of h therefrom. That value of h you can now write this one as integral I naught square r by 2 into 1 minus cos 2 omega t into dt between the limits 0 and t by 2 again. When you integrate this one, taking this as first equation, and the same h we can write in terms of RMS value this way, IRMS square into r into t, I can take that as the second equation. Integrating this one and equating that one with this equation, we finally will be getting the value IRMS is equal to I naught by root 2, which of course we can write this one as 0.707 I naught. That is the corresponding value. Of course, this is a basic integration, that's why we need not discuss to the core. Direct integrate this one will be getting the value of h there. That h value equating to this equation, that is I RMS square into RT, we ultimately can come to the conclusion that IRMS is going to be I naught by root 2, which again can be written 0.707 I naught as such. So this is the equation for RMS value of current. Similarly, we can even write ERMS also in the same manner as E naught by root 2, which also is equal to 0.707 E naught as such. So these two are two pairs of equations, in fact formulae one should remember. One for average value of alternating current, one for average value of alternating EMF, one for virtual value or RMS value of current, and the other one for virtual or RMS value of alternating EMF. So after taking these four, we people have to discuss about different circuits of AC. The very first one, of course, resistance circuit, pure resistance. Similarly, pure inductance, pure capacitance. Then we will be having the combinations like CR circuit, LR circuit, LC circuit. That means in pairs we have to consider. Then coming to the final one, that is LCR series circuit. In all these circuits, we have to understand what will be the value of EMF, what will be the value of current, and what is the phase difference between the EMF and the current there, and what is the phasor diagram for that, and what is the wave representation for those equations. These are the areas we have to concentrate much on. Let us consider resistance circuit of AC. Pure resistance we are taking up. One resistor over here is now connected across an AC source. This is the symbolic representation we all know. E is equal to E naught sin omega t, that is the input EMF supplied to that, and this is the value of R, which is the resistance there. Now when I consider this equation, E is equal to E naught sin omega t, this gives the instantaneous EMF across the circuit when the time is taken as a t. Out of that, E naught gives us the peak value of EMF. Sign represents the function. It's fine. Now, if I just divide the total equation by the resistance of that conductor, then we be getting the equation this way. E by R is E naught by R sine of omega t. But according to Ohm's law, E by R, that refers to the current. In this case, it is to be called instantaneous value of current. That now becomes I naught into sine omega t. So, when you consider this I naught, this is the peak value of current. This is instantaneous value of current. This is my second equation. So, the EMF across this resistor is going to be this much. Current that is across the system in terms of the peak value is going to be this much. When we simply compare these two, this phase and this phase angle both are one and the same. Both the functions are equal. So, there is absolutely no difference in the phase of EMF and current. So, what one can identify from these two equations? Current and EMF both are in the same phase. That is the one we have to understand. That means the phase difference between them is to be taken 0. When their phase is same, phase difference automatically will be 0. But how can we represent this one in the form of wave diagram? Suppose if I consider this as the time and this as either the current or EMF, then I will be getting here a sinusoidal waveform for the value of E is equal to E naught sine omega t. That particular wave represents the EMF, which in terms of the peak value of alternating EMF as well. Whereas when we consider the second equation, this also is a sinusoidal wave equation. But the magnitude of I and magnitude of I naught will certainly be less than the magnitudes of E and E naught respectively. Reason is this: I, of course, we are getting as E by R. Usually the resistance here is going to be more. Then naturally E by R is going to be less when comparing to the value of E. So, we can represent the value of current by this graph. This dotted graph, whatever we are taking up, that represents I is equal to I naught sine omega t. But observe carefully, both the graphs are starting from the same point and ending at the same point only. So, one can understand by look, there is absolutely no phase difference between the alternating current and alternating EMF when we apply or when we observe pure resistance circuit of AC. Same structure in terms of a phasor diagram we can represent in a different manner. Now, let us consider this one as x-axis and this as y-axis. I just consider this first equation first. E is equal to E naught sine omega t. The phase in this equation is omega t. So, I now can write that value of E, virtual value, is going to be like this, and this angle is going to be omega t. So according to this pure resistance circuit, the virtual value of EMF, which of course is also called RMS value of EMF, that now can be at an angle omega t with respect to the horizontal. And we know pretty well in this case of the second equation, both have the same phase. There is no phase change or difference between them. Therefore, the corresponding value of virtual value of current or RMS value of current, that also will be along the same direction of virtual value of EMF. So when once you are observing that IV and EV are on the same line in the same direction, one can reiterate that the phase difference between EMF and current is 0. They are in the same phase. And what is this angle? Phase angle omega t with respect to this x-axis, it's making an angle like this. So this is the one should remember as far as exclusive pure resistance circuit of AC. This is the resistance and this one is AC source, and we people are finding E naught sin omega t is equal to E, that is one equation. I naught sin omega t is equal to I, the second equation, without having any phase change or difference between them. So this is the first circuit one should remember. Let us take the second circuit now, where we are considering a pure inductor, only inductor circuit of AC. So inductor circuit of AC. Let us consider here an inductance coil which now is connected across a source of alternating EMF is equal to E naught sin omega t. This of course we represent it by L. And what is going to be the potential difference across this or EMF across this one? Minus L di by dt. Minus L di by dt, that is actually the EMF across the inductance coil. Now how to reproduce the same equation in terms of EMFs? Look at this one, E plus minus L di by dt, we can write that one as 0. That is the effective value of EMF what we people are considering. What we are considering, the effective value is like this. This can be written this way as E is equal to L di by dt, where from you can write E by L is equal to di by dt. In other words, di can be written as E over L dt. But every one of us can identify from the circuit that this instantaneous value of EMF in terms of the peak value can be represented by this equation. So we can write now E as E naught sin omega t by L into dt. That is actually the concept. Now we want the value of current from this equation. So simply integrate that one. This implies now I is equal to E naught by L integral sin omega t dt. We can rewrite the same equation this way: E naught by L cos omega t by omega. That is actually the integral value for it with a negative sign. If you just consider the same equation this way, E naught by L omega into minus cos omega t, we can write this one as the current I now. But mathematically, minus cos omega t can be written as sin of omega t minus pi by 2. So what can we write here? I is equal to E naught by L omega sin omega t minus pi by 2. This is the ultimate equation for us. But when once we look at this equation, it is similar to I is equal to I naught sin omega t minus pi by 2. What is this I naught here we are finding? If I write the same equation as I is equal to I naught sin omega t minus pi by 2. Here we can say where I naught is equal to E naught by L omega. But in true sense, current is equal to EMF by resistance. That is according to Ohm's law. Now whatever is in the denominator of this equation now should be equal to the resistance offered by that inductance coil. So what can we write now this one as? E naught by XL, we represent this one with. What is this XL now to be called? It is called as inductive reactance. Inductive reactance is nothing other than the resistance that was offered by the coil that is connected in the circuit. It is represented by XL and its formula is going to be L omega, and we can even rewrite the same this way: L into 2 pi f. Omega can be written as 2 pi into linear frequency. The same equation you can even write it like this also: L into 2 pi by capital T, where capital T refers to the time period. So when once we look at this equation and compare that equation with this, E is E naught sin omega t, whereas I is I naught sin of omega t minus pi by 2. So what should be the observation? Current is lagging behind EMF by how much? By pi by 2 radian. So you can come to the conclusion in the case of pure inductance circuit of alternating current, EMF leads the current by pi by 2 radian, or current lags behind EMF by pi by 2 radian. Therefore, when we just plot the graphical representation, you will find one graph directly as a sinusoidal one, which is for E is equal to E naught sin omega t. This is the time axis we are taking up, and this one is EMF axis or current axis. Anything of course you can take. Whereas when once we draw this corresponding graph, the graph corresponding to this equation for current, you will be getting that graph this way. You can guess this one as 0, this one as t by 4, this one as t by 2, this one as 3t by 4, this one as t. That means you will be finding that from this graph, this value of I naught sine omega t minus pi by 2, this is lagging behind EMF by pi by 2 radian. Directly you can understand from that graphical representation. Exactly in the same manner, when I just consider the phasor diagram, again the same way we used to take up. This is x axis, this is y axis, and we represent this one is the virtual value of EMF, which of course is at an angle omega t with the horizontal. Till that extent, it is just similar to the phasor diagram what has been considered in pure resistive circuit. But what else we want? We just have to consider the current also. But according to this equation, current is lagging behind EMF by pi by 2 radian. Therefore, you will be getting a line this way. This is the virtual value of current, and this angle is now going to be pi by 2. So, when we consider the phasor diagram, this line represents the virtual value of EMF, this line represents the virtual value of current, angle between these two is 90 degrees or pi by 2 radian, and this angle being omega t, the difference between them will be pi by 2 minus omega t, which of course according to this equation, since we are having a negative sign here, we have written that one as a sine of omega t minus pi by 2. So, by looking to these two, one can reiterate that EMF is leading by pi by 2 radian in the case of pure inductance circuit of alternating current. So, this is the second one what one has to remember. And only point we need to understand here is these two formulae. This is for EMF, this is for current, and by looking to that equation you can understand that current is lagging behind EMF by pi by 2 radian as such. Let us now take capacitance circuit of AC. We have already discussed resistance circuit, exclusive inductance circuit. Now, exclusive capacitance circuit we just want. So, when we consider a capacitor is connected across the source of AC, which of course is represented by E is equal to E naught sin omega t, and this is the value of C. But we know C is equal to Q by V. Thereby, the potential difference across that one V is equal to Q by C we can write. So, what one can understand here is Q by C must be equal to E according to this circuit. In other words, Q can be written as CE. At the same time, C into E naught sin omega t, that is the input EMF what has been supplied to the system. We now can differentiate this one. dq is equal to C E naught Now we have to differentiate that one with respect to time. This now becomes omega cos omega t. Therefrom I can write the same this way, dq is equal to E naught by 1 by c omega. I write it this way. If c omega comes to the numerator, automatically that becomes E naught c omega only. So it is E naught by 1 by c omega into cos omega t. That is the formula. But of course, this can be rewritten this way. dq is equal to E naught by 1 by c omega. This cos omega t can now be written as sin of omega t plus pi by 2. So when we people are directly differentiating this one with respect to time, this rate of flow of charge, we call that one as current. So what is the ultimate equation? I is equal to I naught sin omega t plus pi by 2. But in place of I naught, what do you have here? If you just analyze that part of it, I naught is equal to E naught by 1 by c omega. But in reality, according to Ohm's law, I should be equal to E by R. That R becomes the resistance there. So here we rewrite this one as E naught by XC we write. And what is this XC now? It is called capacitive reactance. In the case of pure inductance circuit, it is called inductive reactance. That was L omega. Now here it is a capacitive reactance. What is its formula now? We can write XC is equal to 1 by c omega. In other words, 1 by c into 2 pi f we can write, f being the linear frequency. This even can be rewritten like this also, t by c into 2 pi. In fact, omega can be written 2 pi by t, where t is said to be the time period. So you can even write it this way also, and XC will have the same units and dimensions of resistance as such. So this is the importance of XC, one should remember, which is called capacitive reactance. But when we look at this equation for current and compare that one with the equation of EMF, check this equation with this now, compare them. Are you not observing the current is leading this EMF by pi by 2 radian now? That only we can show in the case of the wave diagram. When I take time here and the value of either E or current, either EMF you take on y-axis or current you consider on y-axis, just plot a graph for the EMF and for the current as well across the system. If you take the graphical representation for EMF, E is equal to E naught sin omega t. This is the curve. It is sinusoidal wave, no doubt. The second one also is in fact sinusoidal only. But there is a phase difference of pi by 2. That also it is leading the EMF by pi by 2, not lagging. In the case of inductance circuit of AC, current is lagging behind EMF by pi by 2. But whereas in the case of capacitor circuit, current leads the EMF by pi by 2 radian. So, what can we write now? The other graph for current now should be plotted this way. This dotted one now gives you I is equal to I naught sin omega t plus pi by 2. So, this is the graphical representation for EMF. This is the graphical representation for the current. By looking to this graph itself, one can understand straight away that the current is leading the EMF by pi by 2 radian. Same if you consider in the case of phasor diagram. When we consider phasor diagram, this being x axis now, this being y axis now, this is the line representing the virtual value of EMF. This virtual value of EMF is at an angle say omega t with x axis. Now we should understand current leads that EMF by 90 degrees. Current leads that EMF by pi by 2 radian. So, how to draw that one? We just have to draw a line which is perpendicular to this, and you have to show this one as virtual value of current. And this angle between these two now to be taken as pi by 2. So, what will be the total phase over here now? Omega t plus pi by 2. So, this is actually the phase angle here, this is the phase angle here. Phase difference between them is now going to be pi by 2 radian as such. So, if you can recollect all the three different circuits of AC, one is resistance circuit, one is inductance circuit, and one is a capacitance circuit. In the case of resistance circuit, both alternating EMF and alternating current are in the same phase. The phase difference between them will be 0. In the case of pure inductance circuit, EMF leads the current by pi by 2 radian, or current lags behind EMF by pi by 2 radian. Similarly, if you consider capacitor circuit, only capacitance, then you find current is leading the EMF by pi by 2 radian, or EMF lags behind current by pi by 2 radian. So, these are the major areas one should concentrate while dealing with alternating current circuits. When we take these circuits further, we find combination of circuits. Like we will be finding RC circuit, another one RL circuit, LR circuit we can call it, CR circuit we can call it, LC circuit. Out of the three, pairs like we used to consider, all in series only, LR series circuit, CR series circuit, like that LC series circuit. After completing that one, we just have to take the major circuit there, which is LCR series circuit of AC, and one should discuss the concept of resonance from that circuit as such.